Welcome back, learners. So now we're jumping on to our second concept, whereby now we'll be looking at the field forces. And remember, those are sometimes referred to as the non-contact forces. So a field force or non-contact force is the force that one object exerts on another without the object being in contact or touching. So this is referred to as action at a distance force. So when two objects are exerting for a force onto each other without those two objects touching, then that is going to be action at a distance, or that force there is going to be a non-contact force or a field force. But should the objects touch, then it's no longer going to be a field force or a non-contact force, but it's going to be a non-contact force. And depending on the examples of forces that we had, it can either be either one of them. So, if there is a 3D space around an object in which the effect of a certain type of force may be felt, this force space is called a force field, and the force is called a field force. So these forces that we're talking about, the non-contact forces or the field forces, we have three main types of them. We have the gravitational force, we have the magnetic force, and then lastly we also have the electrostatic force. So all of these three forces are acting at a distance. So those forces are always acting at a distance without the two objects having to touch each other. So you're going to be looking at them individually and see what each of them is and how does it happen. Starting with the gravitational force. Around any object that has mass, there is gravitational field, in which another object with mass experiences a force. The force can act over a distance, and this is only attractive. So we're saying that around any object that has mass, we have something called a gravitational field, in which another object with also having mass will experience a force, and then that force will always act at a distance. It is only attractive. So the gravitational force of attraction between the sun and planets is strong enough to keep the planets in their orbit. So remember now the solar system. We have the sun at the center of the solar system, and we have the planets that are orbiting the sun. Now the force of attraction between the sun and all those other planets keeps the planets in orbit, in their orbit. Should we now, if possible, if we were to switch off that gravitational force, those planets that are orbiting the sun will move out into space and will go into different directions. They will not be keeping their orbit anymore. However, if only it was possible that we switch off the gravitational force. We also have a weaker gravitational force of attraction between the individual planets. So any two objects that have mass will experience a force between themselves, and that force is only attractive, as we have said. So between planet Earth and planet Mercury, and between Venus and other planets, there's always going to be that force of attraction between the two planets. Remember, the force doesn't mean that those two objects have to touch each other. We don't have to touch the sun. We are away from the sun. However, there is that force of attraction between the sun and the planet Earth. So as we can see, the force between the planet Earth and the sun, it is acting at a distance. In continuation with the gravitational force, the Earth exerts a gravitational force of attraction on the moon. So we have the moon that we see on a nightly basis. Now the force of attraction, there's a force of attraction between the Earth and the moon, and remember, for every action, there's an equal but opposite reaction, as we have said. If the Earth applies a force onto the moon will apply the very same force onto the Earth, but then in an opposite direction. Remember, the forces are always acting in pairs. So this force pulls the moon towards the Earth so that it moves around the Earth in an orbit. Same thing applies with the sun and the planet. The force of attraction pulls those planets towards the sun and keeping them in orbit. Now the Earth exerts a gravitational force of attraction on any object on or near its surface within its gravitational field. So the gravitational field, that's now the space around an object that has a mass. So this is called weight. So this object, or this force that is exerted on an object that is on or near the surface of the Earth, this force is going to be called weight. So it's a weight of an object, and the effect of this force is evident in the fact that objects in the air fall to the ground and remain there. So because the objects that are in air, they always come back to the ground. So what goes up always comes down. And because of that force, it is evident. So the gravitational force of attraction between people or objects with relatively small masses is so small that its effect cannot be observed. So whenever you are working with your friends or whenever you're sitting somewhere close to someone, there's always a force of attraction between you and the person that you're sitting next to, or between you and the person that is around you. Remember, around the field, the space that an object has around itself, it is called a field. And then anything that is around or in that field will exert a force of attraction to the other object within that field. So the size of the gravitational force of attraction between two objects depends on these things: the masses and also the distance. So it depends on the mass. That means now the greater the masses of the objects, the greater the gravitational force of attraction between them. However, when talking about the distance, the distance between their centers, the greater the distance between their centers, the smaller the gravitational force of attraction between them. That simply means when we have two masses and we have smaller masses again, so the force of attraction between these two objects is going to be greater than the force of attraction between these two objects, because these two objects have a greater mass as compared to these ones. So if this was 3 kg and let's say 4 kg, and this was 1 kg and 1 kg. Because the mass between these two objects is greater than the mass between these two objects, then the force of attraction here will be much greater than the force of attraction there. However, with regards to the distance, the further the objects are away from each other, if we have object A here and object B there, and we have object C here and object D there, the distance between A and B is smaller than the distance between C and D. So the further the objects are away from each other, the smaller the force of attraction. So the closer the objects are towards each other, the closer the objects are to each other, the greater the force of attraction. So with regards to the distance, as the distance increases between two objects, the force of attraction decreases. But as the mass of the two objects increases, the force of attraction is also going to be increasing. So gravitational force is measured in Newton. Remember, force. Force is measured in Newton and with a capital letter N as the unit of measure. So the mass and weight of an object in everyday language, remember, we are using these two words interchangeably, but they are not the same. In everyday language, mass and weight are often used interchangeably, but in science, they are two different terms with two different meanings. So the mass is actually the amount of substances that are making up that particular object, whereas the weight is defined as the mass multiplied by the gravity. So the weight is defined as now the mass of an object multiplied by the gravity. But remember, in our everyday language, we are using these two words interchangeably, but in science, those two words, they mean two different things. Now going to the next force, being the magnetic force. We need to know that around all magnets, there is something called a magnetic field, in which a magnetic force is going to be exerted. So magnetic force acts over a distance, and it thus a field or a non-contact force. So because the magnetic force also acts over a distance, we can then say that it is a non-contact force. Now this force can also be either attractive or repulsive. But remember, with the gravitational force, it is only attractive. But with a magnetic force, it can either be attractive or repulsive. Magnetic force or magnetism is used to distinguish between magnetic and non-magnetic substances. So substances that are attracted by magnet are known as magnetic substances. And substances that are not attracted by a magnet are referred to as the non-magnetic substance. So this object, because it is attracted to the magnet, is going to be called a magnetic substance, because it is attracted to a magnet. So, with regards to the magnetic field as the space around a magnet, so a magnetic field is an invisible force field in which a magnetic force is exerted. So the space around this particular magnet is called your magnetic field. So within this space, the force can be exerted there. So all magnets are surrounded by a magnetic field that stretches around in all directions. It is thus a three-dimensional field. So all around this particular magnet, we have this space called the magnetic field, and in that field, a force can be exerted. So a magnetic field is invincible, but can be detected by observing the pattern that the iron filling makes around the magnet. So remember that iron can be attracted to the magnet. It can either be attracted or repelled around the magnet. So we can notice that space if we were to put the iron fillings around or in that space. Furthermore, the iron fillings arrange themselves around the magnet along lines called the magnetic field lines. So these lines that we are seeing here are called the magnetic field lines. So we use the magnetic field lines to represent the magnetic field on a two-dimensional paper, because we know that we cannot actually draw things in 3D on a piece of paper. We cannot draw the lines in 3D on a piece of paper. So that means now, the denser or closer the magnetic field lines to one another, the stronger the magnetic field. So the more lines we have closer to each other, the stronger the magnetic field. So it is the strongest at the poles. So around the poles, as we can see, the lines, they are dense. There's more lines around the poles. And as you're moving away from the poles, there's more lines around the poles. And moving away from the poles, the lines, they start to spread and move away from each other. And therefore, in that case, they are not the strongest. Now, those field lines, when you are drawing them, they should never touch or cross each other. Now, the direction of the field lines is from north to south. As we can see, the field lines are always moving from north and going to the southern side. So from the north, the field lines or the arrowheads are showing that they are moving away. Then on the southern side, they're moving towards south. So this is called this is the direction in which a compass needle with the end pole is placed in that field. So that is going to now be showing the direction using the compass needle. Then the last force that you're going to be looking at is going to be our electrostatic force. Now, this comes about when we're talking about atoms. We do know that atoms are always made up of three subatomic particles, which are the protons, the neutrons, and the electrons. And in the nucleus of an atom, we find the protons, which are positively charged, and we find the neutrons, which are neutral particles. They are neither positive nor negative. However, we also have something called the electrons, and those ones, they form a cloud around the nucleus, and they are always negatively charged. So in a neutral atom, we know that there should always be an equal number of protons and electrons. So if an atom is neutral, it needs to have the equal number of protons and neutrons. So a neutral object consists of neutral atoms. And remember, neutral atoms consist of equal number of protons and electrons. Then an object that has an excess of electrons, that means it has more electrons. That means it is going to be more negatively charged, because in a neutral atom, we have protons that are equals to electrons. So should a certain atom have more electrons, that means the overall charge of that atom is going to be a negatively charged atom. So an object that has a shortage of electrons, that means it has more protons than electrons. And protons, as we have said, they are positively charged. So should an atom have more protons than electrons, therefore that atom is going to be positively charged. But should an atom have more electrons than protons, then that atom is going to be negatively charged. So charges or charged objects that are placed near one another have something called an electrical potential energy and exert a force on one another. Now, this electrostatic force that you're talking about here is an example of a non-contact or a field force. Remember, non-contact means the objects do not have to touch each other. The energy comes from the work done by the friction process. Remember friction, that's now two objects rubbing against each other, and the frictional force is always opposing the motion. So the electrostatic force is the attracting or the repelling forces between electric charges near one another. Now that means when we have a proton and a proton, so they have like charges, or an atom that is more positively charged, or an atom that has more protons, and another atom that also has more protons. Those two atoms are positively charged because both of them, they have more protons than electrons. Now those two atoms are going to have like charges, and we know that like charges repel each other. That is now a positive and a positive, or looking at a negative and a negative. However, when looking at two oppositely charged particles or two oppositely charged atoms, that one of them has more protons than electrons and the other one has more electrons than protons, now those two atoms are going to be attracting each other. That's now we're saying that opposite charges like a plus and the minus, they are going to be attracting each other. So now remember, we have three types of non-contact forces. We have the gravitational force, we have the magnetic force, and then lastly we have the electrostatic force. And I hope you know what each of those forces entail and how do we actually get those forces. So until I see you next time, goodbye.